a, b, n are all integers, and n is a positive integer, and a doesn't equal to b. And if n divides a to the power of n minus b to the n, then can we show that n also divides the original expression divided by a minus b? First, we let a minus b equal to t. Right? So in other words, a becomes b plus t. So a to the power of n minus b to the power of n over a minus b becomes b plus t to the n minus b to the n over t. So using binomial expansion. After that, the first term will cancel with this term and also simplify with the t. And so after everything, we have k starts from 1 to n, because the first term already canceled. So n choose k times b to the power of n minus k. And t to the, instead of k, we have k minus 1, right? Cancel with this t. So when k equals 1, first term is n times some integer, right? That is obviously divisible by n, right? So we only look at when n equal greater than equal to 2. Right? Every single term in here, right, can be every single term times t. In fact, can be written into, if we rewrite this combination number into n over k, right, let's just quickly, so n minus 1, choose k minus 1, right? This can be easily verifiable, times b to the n minus k times t to the k minus 1. Right? So here I just rewrite n into unique prime decomposition. P1 to the alpha 1 times P2 to the alpha 2 all the way PR to the alpha R. Every alpha is a non-negative integer, positive integer. And all those P's are unique, uniquely distinct. And so that for those P that doesn't divide A minus B, right? Of course, P to the alpha also doesn't divide A minus B. Then we can say for those powers of primes, they must divide. They must divide a to the n minus b to the n over a minus b. The reason is because a to the n minus b to the n can be written into a minus b times a to the n minus b to the n over a minus b. As long as p to the alpha doesn't divide a minus b, right, it has to divide the other term, the other factor. Right? This is because of the fundamental theorem of arithmetic, right? Unique factorization. Right? So those primes are fine, nice P's, nice primes. But for those P's that P actually divides A minus B, I'm using T in this case. What happens? Right, can we also show that P to the alpha divides this term? Can we? First of all, I'm going to copy the middle terms and then rewrite N, K, and T. Right? So copy those terms. Right? N minus 1 choose K minus 1 times B to N minus K times N over K times t to the k minus 1. Like I said, first let me rewrite n into m1 times p to the alpha. Here alpha is some fixed number, right? Any fixed. So here I choose perhaps p3 to the alpha 3 fixed. I rewrite it into this term. So in which case p does not divide m1. M1 doesn't contain any p. Right? All the p's are here. Right? Likewise, I just rewrite k into m2 times p to the beta. Likewise, m2 p doesn't divide, m2 doesn't contain any p. And I also rewrite t into m3 times p to the gamma. P doesn't divide m3. Okay? So this is already an integer, right? Combination number, right? Integer, doesn't matter. I rewrite it into some m4. Right? M4. N over k. m1 times p to the alpha. K becomes m2 times p to the beta. T becomes m3 raised to the power of k minus 1. P to the gamma times k minus 1. Right? So I have m4, m1 over m2. I'm going to combine the p's, of course, times m3 to the k minus 1. And all the m's are here, right? All the p's, p to the alpha minus beta plus gamma times k minus 1. Right? Right, we're going to discuss these m's later. Now we're going to focus on the power of p, right? Determining its size. So hopefully it has at least alpha many p's. Right? So first, what's the size of beta? I say beta is no larger than k. Right, so this k. Beta is no larger than k. Why? Because p to the beta equals one plus s to the beta, right? P is a prime, at least it's 2, so s is at least 1. Okay? So binomial expansion, 1 plus beta times s, 1 plus the other terms. S to beta, last term. So S is at least 1. So that's at least 1 plus S. 1 plus beta. I replace S with 1. I get rid of so plus S to beta. Right? Get rid of the 1. Strictly greater than beta. Right? And also, p to the beta is just part of k, so can no larger than k, right? Be no larger than k. So, like I said, here k is at least 2. Right? 2, 3, 4, 5. So, if beta was equal to 0, right? Of course, beta is strictly less than 2, 3, or 4, 5, doesn't matter. If beta is equal to 1, obviously true. 1 is strictly less than 2. If beta is 2, 3, 4, 5, at least 2, then of course I at least have 3 terms here. Right? Get rid of the other terms. Only left with this term. Right? Strictly loosened. Right? Beta is strictly less than k. Right? So in other words, negative beta is strictly bigger than negative k. Right? So when I look at the power, first of all, I can say that, right, this power, alpha minus beta plus gamma times k minus 1. All right, first of all, it's strictly bigger than, so replace negative beta with negative k. Right, alpha minus k plus. All right, so gamma times k minus 1. Right, what happens with gamma? Right, so like I said, for those p that divides t, right, so t contains at least 1 p. Right, 1, 2, 3, at least 1 p. And so gamma is at least 1. Gamma is at least 1. So gamma times k minus 1 is at least k minus 1. K minus 1 is positive, of course. Right, so that this cancel out. Alpha minus 1. So that's what happens with the power. The power is, right, strictly larger than alpha minus 1, which means it could be equal to alpha. Right? Strictly larger than alpha minus 1 could be equal to alpha. So greater than equal to alpha. So really, this term contains at least alpha many p's. Right? So the question is, what happens to this term? Right? If it's an integer, then it's fine. Right? So that means it's a multiple of this many p's. Right? At least alpha many p's. But what if this is a proper fraction, right? So which means after all the simplification between this m2 bottom and these, positive, this integer at the top, right? We still have some primes down on the bottom that cannot be simplified with this, right? Some p's, some product of some p's. Right, which might be different than these p's, right? But because this whole term, right, that is this term, obviously an integer. Yeah. Right, so that means since after simplification, the bottom cannot be simplified with the top anymore, which means in order for it to be an integer, right, the bottom has to somehow simplify with this. Right? Otherwise, it will be just a fraction, right? Cannot be an integer. Which means the bottom, in the end, has to contain some p in order to simplify with this, right? Which is impossible because, like I said, I just rewritten k into m2 times p to beta, where m2 doesn't contain any p. Right, so cannot happen. So this whole thing must be an integer. Right? So in the end, every term in here is a multiple of at least alpha many p's. Right? So for those not so nice p's, right, we eventually can prove that those p's, right, for those p's, as long as p divides a minus b, then accordingly each p to the alpha, each power of p in here must divide each term here, right? I obviously divide the sum of these terms, right? Sum, that is this one, right? Divisible by those p to the alphas. Right, so plus, previously we've shown that for those nice p's, right, nice ones, right, those who doesn't divide a minus b, they must divide p to the alpha. They must divide this. Right? So whether it's the nice p's, not so nice p's, right, the power of p's, every power of p's must divide this. Right? And we're done.